let's just dive right in. For what, almost a century now, theoretical physics has had this one almost mythical goal.
Quantum gravity.
Quantum gravity. It's the final piece of the puzzle, right? The grand attempt to make Einstein's theory of space-time general relativity.
Which is all about the big, smooth, cosmic scale.
Talk to the completely bizarre probabilistic world of quantum mechanics.
The rule book for the very small.
And we've been chasing this theory of everything for 50 years. And the honest truth is, we've hit a wall, a really big one.
That is the honest assessment. I mean, if you look at the history of physics, it's this beautiful story of unification.
Right.
Newton connects the apple falling from the tree to the moon orbiting the Earth.
Yeah.
Maxwell unifies electricity and magnetism.
Then the Standard Model comes along and wraps up 3 of the 4 fundamental forces.
The strong, the weak, and the electromagnetic, all under this quantum field theory umbrella. So quantum gravity, bringing Einstein's theory into the fold, it feels like the necessary next step, the culmination.
But the path we've been on, that whole journey, has been dictated by one single incredibly powerful assumption. You call it the quantization dogma.
It is the absolute core belief that has driven almost all mainstream research since the 70s. The dogma is simple. Gravity must be created just like the other 3 forces.
Okay.
And since those forces are quantized, they're mediated by particles, photons, gluons.
Little messengers.
Exactly.
Yeah.
Then gravity must also have its messenger particle, the graviton. And that means space-time itself, at the tiniest possible level, must be all jittery and quantum.
That seems logical on the surface, doesn't it? If all the actors on the stage, all the matter and forces are quantum, then the stage itself, space-time, should be quantum too. So why are we now calling this a crisis?
Because after all that time, all that brain power, the 2 giant theories built on that dogma string theory and loop quantum gravity have given us?
Well, nothing.
Nothing definitive. Nothing definitive. No verifiable predictions we can actually go out and test. 50 years of beautiful math and empirically silence. And that silence isn't just frustrating. It's starting to feel like a signal that we took a wrong turn somewhere.
And that silence, that vacuum, is where the interesting stuff starts to happen. So this deep dive is about the heretics. It's about the radical question that's finally being asked out loud. What if that foundational assumption that gravity must be quantum is just wrong?
What if the stage is fundamentally different from the actors?
Exactly, and we're seeing 2 massive shifts happening at once. The first is theoretical, the rise of this new idea, post-quantum classical gravity, which says gravity stays classical.
And the second is experimental.
Yeah.
The whole game has moved from dreaming about giant colliders to these incredibly precise tabletop experiments.
Including a huge discovery in 2024, which we'll get to, where they found something that looks and acts just like a graviton, but on a tiny chip.
It's a fascinating time.
It feels like physics is trying to do a full system reboot, so I think we have to start by understanding why the old programs crashed. Let's look at the old guard strings and loops and the fatal flaws that led us to this point.
To really get the boldness of the new ideas, you have to appreciate just how deep the problems with the old ones really are. Let's start with the big one.
String theory. I mean, for most people, if they've heard of a theory of everything, this is it.
It is. It captured the imagination for a reason. The central idea is just so elegant.
That everything, every particle, every force is just a different note played on a tiny, vibrating, one-dimensional string.
It was an incredible idea. And the promise was this profound unification. The math, almost magically, required a spin 2 particle to exist.
Which everyone immediately said, that's the graviton.
Exactly. It wasn't bolted on, it just fell out of the equations. Gravity was woven right into the theory from the start. The mathematical beauty was just irresistible.
It promised the answer. A single, unique description of the universe. So where did it all go wrong? Where did that beautiful math lead us astray?
It led us to something called the landscape problem.
Right.
So, for the map to work, string theory needs more dimensions than the 4 we see, usually 10 or 11.
So the extra 6 or 7 have to be curled up, hidden away somehow.
Right, curled up into these incredibly complex little shapes called Calabi-Yau manifolds. And the hope, the absolute driving hope, was that the theory would force them to curl up in only one specific way.
Giving us our specific universe with our specific laws of physics.
The unique solution, the Holy Grail. Instead, what they found was a nightmare.
They found that there wasn't just one way for them to curl up.
There were, by some estimates, up to 10 to the power of 500 possible ways.
10 to the 500. I mean, just to put that number in perspective for you, it's a 1 with 500 zeros.
Yeah.
It makes the number of atoms in the observable universe look like a rounding error.
It's a functionally infinite number, and that is a devastating critique. Each one of those possibilities, each vacuum, describes a different universe.
With different particles, different forces, different constants.
A theory that describes every possible universe explains no particular universe. It loses all its predictive power. You can't test it, because any experimental result you get, you can just say, oh, well, that's just the physics in our little corner of the landscape.
And this is what led to that really controversial defense, right? The anthropic principle.
It's seen by many as a complete retreat from the scientific method.
Can you just walk us through why that's so damaging, really?
The anthropic principle basically says, well, of course we live in a universe with physical constants that allow for life to exist. If they were different, we wouldn't be here to ask the question.
Which is logically true.
But it's not an explanation. It's an observation. The job of fundamental physics is to explain why the constants are what they are, not just to say we're lucky to be in a universe where they are what they are. It replaces prediction with postdiction.
Is giving up.
It feels like it. It's a philosophical backstop for a theory that stopped making physical predictions.
And beyond the landscape, there's another, maybe even deeper, theoretical problem that goes right to the heart of what Einstein taught us: background dependence.
This is a really crucial point, especially when we get to loop quantum gravity. The whole lesson of general relativity is that space-time isn't a fixed stage.
It's a dynamic actor. It bends and warps in response to matter and energy.
Exactly. The stage itself is part of the play. And yet, the most successful and calculable versions of string theory have to start by assuming a fixed, flat, boring background spacetime, usually Minkowski space.
So to even get the theory off the ground, you have to ignore Einstein's most profound insight.
You do. The theory of quantum gravity should produce spacetime, not be defined on a pre-existing spacetime. It's a deep, nagging conceptual flaw.
Okay, so that very flaw, that background dependence, is what string theory's main rivals set out to fix.
Loop quantum gravity, or LQG.
And its promise was a truly background-independent theory.
That was its entire reason for being. LQG tries to quantize general relativity directly. No extra dimensions, no strings, just take Einstein's equations and make them quantum.
And in this theory, space itself is made of discrete little bits.
It's woven from these tiny interconnected loops or threads in what's called a spin network, so area and volume aren't continuous. They come in fundamental, indivisible chunks. The smallest possible area, the smallest possible volume.
The geometry of space-time is quantum from the ground up. I mean, that sounds amazing. It's like building the stage out of those Lego bricks we talked about.
It is an incredibly appealing idea.
So what's the catch? What's the big failure point for LQG?
The big one is called the continuum limit problem.
Okay.
If space is made of these discrete Lego bricks at the tiniest scale, you have to prove mathematically that when you zoom way out, it all smooths out perfectly to look like the continuous flowing space-time of Einstein that we actually observe.
You have to prove that your pile of bricks looks and acts exactly like a smooth fluid.
And that proof has been incredibly elusive. It's a huge mathematical challenge, and without it, you can't be sure that LQG actually describes our universe at large scales. That uncertainty hangs over the whole project.
And it has the opposite problem to string theory when it comes to matter. Right?
Exactly.
Yeah.
It's the inverse problem. String theory naturally gives you all the matter particles. They're just different vibrations of the string.
They're part of the package.
LQG, because it's so focused on quantizing geometry, has always struggled with how to include the particles of the standard model. You sort of have to add them in by hand.
So you have this beautifully quantized stage, but the actors feel like they were tacked on as an afterthought.
Right, the sense of unification is much weaker. You've got a theory of quantum space, but it doesn't really explain the stuff in that space.
So we're left with this choice. String theory, which unifies everything but gives you an infinite number of universes and compromises on Einstein's core lesson.
Or loop quantum gravity, which respects Einstein but can't prove it looks like our universe and doesn't naturally include matter.
And both of them, at their heart, are chained to that same initial assumption.
The quantization dogma. Both start by saying gravity must be quantum.
And when both of your main approaches run into such fundamental show-stopping problems, maybe it's not the approaches that are wrong.
Maybe it's the starting assumption. Maybe forcing gravity, which is space-time, to play by the same rules as the forces in spacetime was the original mistake.
Which is where the heretics come in. If the high priests of physics failed, it's time to talk about the thinkers who decided to burn the dogma down. And this is where the story gets really radical. The idea, championed by people like Jonathan Oppenheim, is, what if gravity just stays classical? What if it never becomes quantum, even when it's interacting with quantum stuff?
It sounds like treason, doesn't it? It completely flies in the face of 50 years of thinking in fundamental physics.
And for a long time, there were very good reasons to think it was impossible. These no-go theorems.
Right, they were considered ironclad.
So what was the barrier? Why did everyone think coupling a classical gravitational field to quantum matter would just break the universe?
The theorems all show that if your classical field was deterministic, if it responded in a smooth, predictable way, you'd create paradoxes.
Like violating the uncertainty principle.
Exactly. A perfectly smooth classical field could, in theory, measure a particle's position so precisely and then its momentum so precisely that you'd know both at the same time.
And that's a cardinal sin in quantum mechanics. It would collapse the whole structure.
It would.
Yeah.
And even worse, some models showed you could use this connection to send signals faster than light.
Another absolute no-go.
So the door seemed firmly shut. If the coupling is deterministic, the universe breaks.
And that word deterministic is the key that Oppenheim picked the lock with.
That's the breakthrough. His huge insight was realizing that all those no-go theorems assumed the interaction had to be predictable. He proved that if the interaction is fundamentally stochastic, if it's inherently random and noisy, all paradoxes just melt away.
So randomness isn't a bug, it's a feature, a necessary one.
It's the core of the whole theory. In this picture, space-time doesn't just respond to the average position of a quantum particle. Instead, the quantum matter makes space-time itself jiggle and tremble randomly.
The metric itself becomes noisy.
Yes, this fundamental fluctuation, this noise, ensures that the classical field can never be a perfect measuring device. It can't pin down a quantum state with enough precision to violate uncertainty or send a faster-than-light signal. The randomness saves the consistency of the physics.
So how do you write the math for a universe like that? You can't just use the good old Schrödinger equation.
No, that describes a closed, reversible, unitary system. You need something totally different. The theory uses what's called a master equation.
And the key thing about a master equation is that it describes an open system. It's non-unitary.
That's the secret sauce. Yeah. Unitary is just a fancy way of saying information is never lost. The process is perfectly reversible, like running a film forwards and backwards.
But a non-unitary system is different.
It's interacting with an environment. There's friction, there's leakage. Information can be lost. In this case, the quantum system is constantly losing information to the classical stochastic gravitational field.
Okay, but how do you do that without the math just breaking down and giving you nonsense like negative probabilities?
That's the clever part of the formalism. The master equation is constructed in a very specific way. It's what we call completely positive and trace-preserving, which is a mathematical guarantee that the probabilities will always behave themselves. You get a consistent, non-reversible evolution.
So by embracing this randomness and information loss from the very beginning, you get a theory that's mathematically sound and describes this hybrid reality.
And out of that consistent coupling comes the theory's most powerful and testable prediction, a fundamental trade-off.
An inescapable tension between two effects, decoherence and diffusion.
This is what makes it real science. It's not just a story, it's a relationship you can go out and try to measure.
Let's start with the first one, decoherence. This is the effect on the quantum world.
So because this classical spacetime is constantly interacting with the quantum matter, it's sort of measuring where the mass is so it knows how to curve, it forces the quantum state to collapse.
It's a universal measuring device.
It's a universal measuring device.
Right.
It is constantly poking and prodding any quantum superposition based on its mass, causing it to lose its quantumness and decohere.
This sounds a lot like a solution to the measurement problem, the whole mystery of why we don't see, cats that are both dead and alive.
It is the aha moment of the theory. The collapse of the wave function isn't some mystical event caused by a conscious observer. It's a physical process driven by gravity.
So a big object, like a cat, has so much mass that its interaction with the gravitational field is so strong
that it decoheres almost instantly. It can never exist in a macroscopic superposition because spacetime is constantly forcing it to choose.
Okay, that's one side of the coin. The flip side is space-time diffusion, the effect on the classical world.
Right. To keep everything consistent, the quantum matter has to kick back on spacetime. And that kick is random. This is the source of the noise.
Space-time diffusion. So the very fabric of the universe is constantly trembling.
It has to be. And the two effects are locked together by a rigorous inequality. The more space-time diffusion or noise you have, the faster the decoherence. The less noise you have, the longer a quantum superposition can survive.
You can't have one without the other.
A noisy, fluctuating space-time is the price you pay for having stable quantum mechanics in the first place.
This idea of a non-unitary universe, one where information can be lost, it has huge implications for another major problem.
The black hole information paradox.
The most famous paradox in modern physics.
For decades, it's been this epic clash between two pillars of physics. Pillar 1, Einstein's general relativity, says information that falls into a black hole is gone forever.
Pillar 2, quantum mechanics, says information can never be destroyed, it has to be preserved, unitarity must hold.
And the entire orthodox search for quantum gravity has been about finding a clever way to save Pillar 2, to get the information back out.
But this heretical theory takes a completely different approach.
It just says Pillar 2 was wrong.
It just gives up on unitarity.
It embraces information loss. Since the fundamental evolution of the universe is already non-unitary and stochastic, there's no paradox to solve. Information gets destroyed by the noisy metric all the time. Black holes are just a particularly dramatic example of it.
Wait, but isn't that a huge break? Isn't information preservation a bedrock principle?
It's a deeply held assumption. And the heretical argument is that this assumption is precisely what created the paradox in the first place. They argue that general relativity was right all along. The process is irreversible. It's our insistence on forcing quantum unitarity onto gravity that was the mistake.
Wow, that's a fundamental shift in how you see reality. It means we live in a universe that's actively forgetting things.
And what's so incredible about all of this is that it's not just philosophical anymore. The whole debate has moved out of the ivory tower and into the lab.
We don't need a collider the size of the solar system. We need a quiet room and a very, very sensitive scale.
Pretty much. And this shift is perfectly captured by this high-stakes public bet.
The bet of the century. Oppenheim versus the heavyweights from the orthodox camps like Carlo Rovelli from LQG and Jeff Pennington from the string theory world.
It's more than just a bet, it's a scientific challenge. The odds are 5,000 to 1.
And the terms are designed to settle the fundamental question: is gravity quantum or classical?
Right. Oppenheim loses his bet if gravity is ever proven to be quantum. And the gold standard proof for that would be an experiment called gravitationally induced entanglement, or GIE.
And he wins his bet if gravity is proven classical, specifically if someone detects that unique signature of his theory.
That random stochastic noise.
Yeah.
The space-time diffusion.
Let's talk about hunting for that noise first. If space-time is really wobbling, how on earth do you detect something that subtle?
The proposals are all about precision measurement. Basically, you take a test mass, a tiny gold sphere, a supercooled pendulum, and you try to weigh it with almost impossible accuracy.
And you're looking for a tiny random jiggle in its weight that isn't caused by anything else.
Exactly. And that's the monumental challenge. You have to shield it from everything. Seismic vibrations, thermal noise, even quantum vacuum fluctuations. The prediction is that you'll be left with a residual, random wobble that can only be explained by the background spacetime itself fluctuating.
Is this actually happening now, or is it still on the drawing board?
Oh, the hunt is on. Experiments using atom interferometry are already sensitive enough to start putting limits on the theory. They can rule out some of the simpler models of this stochastic gravity.
So the experimentalists are already tightening the screws on the theorists.
Which is exactly how science should work. It forces the theory to be more precise and predictive.
Okay, so that's the test for the classical side. What about the other side of the bet, the definitive quantum test?
Gravitationally induced entanglement, GIE. This is the experiment that the quantum gravity proponents believe will prove them right.
What's the procedure? How does it work?
Conceptually, it's pretty elegant. First, you take two tiny massive particles, like microdiamonds, and you put each one into a quantum superposition of being in two places at once.
So you've got two tiny Schrodinger's cats.
Exactly. Then, you place them very close to each other, carefully shielding them from every force except gravity. They can only feel each other's gravitational pull.
And then you just see what happens.
You see what happens. And the interpretation all hinges on a core principle of quantum information called LOCC.
Local operations and classical communication.
Right, which basically says you can't create entanglement between two systems using only a classical channel. If I want to entangle a particle in my lab with one in yours, I have to send a quantum particle, like a photon, between them. A phone call won't do it.
So if you run this experiment and the two diamonds become entangled,
It means the thing that connected them, gravity, must have been a quantum channel. It must have transmitted quantum information. That would be the smoking gun for a quantum graviton.
and if they don't get entangled, if instead they just decohere and their superpositions collapse.
There would be incredibly strong evidence for Oppenheim's theory. The noisy classical field would have destroyed their quantumness before entanglement could ever form.
It really feels like a definitive showdown.
It is, although there are some recent theoretical wrinkles suggesting some very exotic classical models might be able to fake entanglement. But for the most part, the community agrees. If you see GIE, quantum gravity wins.
So the whole debate seems to come down to these two experiments. But the legendary physicist Freeman Dyson threw a wrench in the works years ago, right? He questioned if we could ever detect a single graviton at all.
It's a brilliant and frustrating argument. Dyson calculated that because gravity is so unbelievably weak, any detector you build to catch a single graviton would have to be absurdly massive.
Like how massive?
Planet-sized. Maybe as big and dense as Jupiter.
And the punchline, the paradox is...
The punchline is that if you actually built a detector that massive and dense and shielded it from all background noise, general relativity says it would collapse under its own gravity and form a black hole before it could ever register a detection.
The act of looking for the particle destroys the detector.
Exactly.
That's incredible. So if the graviton is operationally undetectable, if the universe itself prevents us from ever seeing one, why build theories based on the assumption that it must exist?
That's Dyson's point. It gives a huge amount of philosophical weight to the heretical side. If the particle is indistinguishable from non-existence, maybe a theory that doesn't need it in the first place is the more sensible, more scientific path.
But what about gravitational waves? We detected those. Doesn't that prove something?
That's a great question and an important distinction. We detected the waves, which are classical ripples in space-time. That's like detecting a radio wave. It doesn't prove the existence of the individual photon. Dyson's argument is about detecting the single quantum of the wave, the individual graviton, which he argues is impossible.
So while this whole debate is raging and experimentalists are building these incredibly sensitive detectors, a completely different result comes out of left field in 2024.
From a condensed matter lab of all places.
The discovery of chiral graviton modes.
And we have to be so clear about this right up front.
This is not the discovery of the fundamental graviton.
Absolutely not.
Yeah.
They did not quantize the universe's gravity in a lab.
So what did they see? What is this thing?
They observed what's known as a quasi-particle. It's a collective emergent phenomenon. You have millions of electrons in a material all acting together in a coordinated way, and that collective excitation behaves, for all intents and purposes, like a brand new particle.
But it's not a fundamental particle. It's an illusion created by the crowd.
A very real, measurable illusion. And in this case, the quasi-particle they found perfectly mimicked the mathematical properties of a graviton. It's a graviton analog.
Let's talk about the setup because it's just wild.
It's extreme physics. You start with a simple gallium arsenide semiconductor chip. You cool it to within a fraction of a degree of absolute zero.
Colder than deep space?
Much colder. And then you hit it with an incredibly powerful magnetic field about 20 times stronger than an MRI machine.
And under those conditions, the electrons inside just stop being electrons in a way.
They stop acting like individuals. They condense into this exotic state of matter called a fractional quantum Hall effect liquid.
Yeah.
They behave like a single coordinated quantum fluid.
And this fluid has properties that the individual electrons don't.
Right. It can do things like carry fractional electric charge, and crucially for this experiment, it develops its own internal emergent geometry.
So how did they see the graviton mode in this fluid?
They used a technique called Raman scattering. They essentially shined a laser on it, but a very specific kind of laser with circularly polarized light.
So the light itself had spin.
It had angular momentum.
Yeah.
They were essentially kicking the fluid with a specific kind of twist, and then they watched how the fluid vibrated in response.
And it responded with a vibration that had spin 2. Let's just unpack why spin 2 is the magic number here.
Spin is fundamental. A photon, which mediates electromagnetism, is a spin 1 particle. It describes a vector field, something with a direction.
Like an arrow.
But gravity isn't just a direction. It's about the curvature and stretching of space-time itself. That requires a tensor field, and the particle for a tensor field has to be spin 2.
And the defining feature of something with spin 2 is that if you rotate it 180 degrees, it looks exactly the same.
Precisely. And that is exactly the symmetry they saw in the vibration of their electron fluid. The collective excitation, the chiral graviton mode, was a spin-2 phenomenon. It was a quantum of a geometric fluctuation within their artificial universe.
So they created gravity-like physics from non-gravitational parts.
Yes, that's the whole point.
Which has enormous implications for this whole idea of emergent gravity.
It's the first empirical proof of concept. The CGM is a perfect example of emergence. You start with spin 12 electrons, you connect them with spin 1 photons, and out of that complex interaction pops a collective excitation that behaves like a spin 2 boson.
You didn't need to start with a fundamental graviton to get gravity.
You didn't. And if you can do that in a lab, on a chip, it gives incredible weight to the idea that maybe the gravity of our universe isn't fundamental either. Maybe it emerges from some deeper, non-gravitational substrate.
The chip becomes a simulator for quantum gravity.
An almost perfect one. Physicists can now change the parameters in the lab, the temperature, the magnetic field, and watch how these gravitons behave, how they interact, how they decay.
You can study quantum geometry in a controlled setting. You don't need to go to a black hole or the Big Bang.
You just need to go to a very, very cold lab. It's a complete revolution in how we can approach these questions.
So we've seen the two orthodox theories hit a wall. We've seen a coherent, testable heretical theory rise up. And now we have experimental proof that the kind of physics it describes can actually happen.
The entire field is shifting under our feet. It's moving away from this abstract theory of everything search.
And towards a world of hybrid theories, condensed matter simulators, and achievable tabletop experiments.
And if the heretics are right, if this post-quantum classical view is correct, then the universe is a very different place than we thought it was.
Let's just summarize that new picture for everyone. If we live in this stochastic universe, what does that mean?
First, gravity is classical. But it's alive, it's dynamic, it's constantly interacting with the quantum world.
Second, the universe is fundamentally noisy. Space-time isn't a quiet backdrop. It's seething with these random fluctuations.
Third, that noise is what makes reality concrete. It's the universal decohering agent that collapses quantum possibilities into the single classical world we see. The measurement problem is solved.
And fourth, information is not sacred.
It's not. The universe is fundamentally non-unitary, information can be lost, and the black hole paradox just evaporates. The laws of physics are not perfectly reversible. The universe can, and does, forget.
It's amazing that we've gone from pure speculation to a series of actual empirical races that are happening right now.
There are three huge experimental fronts that will define the next decade.
First is the direct hunt for space-time diffusion.
Right, weighing the vacuum, trying to get our scale sensitive enough to isolate that tiny gravitational wobble.
Second is building better simulators, using these quantum Hall systems to really dig into the mechanics of emergent geometry.
And the third, the biggest one of all, is the GIE experiment, the ultimate decider.
Can gravity entangle two masses?
That one experiment could either vindicate 50 years of orthodoxy or prove the heretics were right all along.
It's funny, the old theories required this almost superhuman, abstract mathematical genius. But the new ones
demand the patient, hands-on, practical ingenuity of the experimentalist. It's a huge cultural shift.
The history of science is full of these moments, isn't it? Where the biggest breakthroughs don't come from finding the final answer, but from having the courage to question the first assumption.
By challenging the dogma of the graviton, these thinkers have opened the door to actual, testable science, where for decades there was only stalemate.
So maybe we should stop thinking of the graviton as this elusive, fundamental particle we have to go out and find. Maybe it's better to think of it as, I don't know, a song sung by the collective motion of the universe.
A song we finally learned how to play on a tiny, super-cooled semiconductor chip.
So what stands out to you? Are you betting on the beautiful math of strings, the discrete fabric of loops, or the trembling stochastic vacuum? The answer might not be out there in the cosmos, but right here, in the quietest, coldest corner of a lab on Earth.